On from Boyle's Law to Charles' Law. Before we talk about Charles' Law, just want to kind of go back and refresh our memory of what we've done so far. We have started looking at gases and said that we had to consider three things when we looked at gases. We had to consider volume, temperature, and pressure. And with Boyle's Law, we looked how volume and pressure are related to each other. We have an inverse relationship where one goes up, the other goes down, so on and so forth. So today we're going to look at Charles' Law. So with Charles' Law, what we have is a direct relationship between volume and temperature. All right, and so before we talk about that, let's kind of think about back when you were younger. In school, you probably had a lab or an activity in science, or maybe you saw this, maybe someone came into your class and did this as a demonstration where you had a balloon blown up and the balloon was placed into something that was a really cold environment, or maybe even liquid nitrogen was placed on the balloon, and the blown up balloon shrunk way down, and then once it was taken out of that cold environment and brought into room temperature, the balloon kind of magically, in quotation marks, blew back up. All right, that's an example of Charles' Law. And what's happening is the particles inside the blown up balloon, remember there's gas particles, they're always moving around. When they're put into a cold environment, they start moving much slower. And then when they're taken out of that cold environment and brought into a warmer environment, the particles start moving around faster again. And you can see how that affects the volume of the balloon. When the balloon was put into the cold environment, the temperature went down, therefore the volume went down. If it was put into the warmer environment, the temperature went up, and therefore the volume went up. And this is what Charles' Law tells us. All right, so again, remember, we have three things we have to consider. We have to consider temperature, volume, and pressure. And again, we have pressure, temperature, and volume. And remember, one of those three elements is going to be a constant. So in this case, our temperature is constant, so we don't really have to worry. Our pressure is constant, so we don't really have to worry about pressure when it comes to calculating our temperature or our volume. So when we look at Charles' Law, we see that if volume goes up, the temperature goes up, or if the temperature goes up, the volume goes up, or we could say it vice versa. As the temperature goes down, the volume goes down, so on and so forth. Here's our formula. We have T1 over V1 equals T2 over V2. Let me write it a little different way. So we have T1 divided by V1 equals T2 divided by V2. So we have temperature and volume that we're looking at. So the other thing we have to consider is that now our temperature is in Kelvin. So we're degrees Celsius plus 273 gives us Kelvin. So we have to make sure that our temperature is always in Kelvin when we're doing these calculations. And of course, volume, V stands for volume. So let's look at a graph here. When we look at this graph, we have temperature here, degrees Celsius, and we have volume here in milliliters. And as our temperature increases, our temperature increased, our volume increased, or if our temperature decreases, our volume decreases. So you can see it's a direct relationship. One goes up, the other goes up. If one goes down, the other goes down. All right, so let's look at this. What kind of relationship do volume and temperature have? At a constant pressure, it is directly proportional. In other words, whatever one does, the other one does the same thing. Temperature goes up, volume goes up. Temperature goes down, volume goes down. Now, let's look at a practice problem. What would be the resulting volume of 4.8 liter balloon at 10 degrees Celsius that was placed in a container of dry ice at negative 78 degrees Celsius? So we have temperature, T1, V1, T2, V2. There's my pen again. All right, so what's my beginning temperature. My beginning temperature is 10 degrees Celsius. Hold on, let me erase that. So we have 10.0 degrees Celsius. My beginning volume is 4.8 liters. My ending temperature is negative 78 degrees Celsius. And my ending volume, well, I don't have an ending volume, so that's what I'm calculating for. Okay, first thing we need to do is change our temperatures into Kelvin, so we add 273 to each one. And here we get 283 Kelvin, and here we get 195 Kelvin. We're adding a negative number, so that's why it's smaller. So let's look at our formula. T1 over V1 equals T2 over V2. Let's plug in our numbers. We have 283 Kelvin over 4.8 liters, and we have 195 Kelvin over our V2. That's what we're calculating. Okay, so this might look a little bit confusing. It's really not that difficult. If we cross multiply each of these, what we end up with is 4.8 times V2 is equal to 283 times 195. We want V2 by itself. We're going to divide by 4.8 on each side. My 4.8's cancel out, so my V2 is going to be equal to 3.3. That doesn't look good. 3.3 liters. Since my volume is liters. Now let's check and make sure that works. Okay, so let's look at this. Our temperature went from 283 Kelvin to 195 Kelvin. So our temperature went down. Therefore, that means our volume has to go down. Let's see if that's the case. Our volume was 4.8 liters to start off with, and now it's 3.3, so yes, it did. So we are okay. Everything works out. Let's try another problem. Here we have a 1,000-liter balloon at 299 degrees Celsius, has a volume, changes to 1,500 liters. What is the new temperature? Now notice here, the new temperature in degrees Celsius, so we're going to have to do a little bit extra. So let's do this again. T1, V1, T2, V2. So our T1 is 299 our degrees Celsius. Our V1 is 1,000.0 liters. Our T2, okay, that's what we're solving for, and our V2 is 1,500.0 liters. Let's change this into Kelvin. So we got to add 273. So that gives me 572 Kelvin. So let's look at our formula. T1 over V1 equals T2 over V2. So let's plug in our numbers. 572 Kelvin over 1,000.0 liters equals my T2. I'm calculating for that, so I keep that there. 1,500.0 liters. Again, we can cross multiply. So 1,000.0 times T2 is equal to 1,500.0 times 572. So I want to get rid of this 1,000 over here. So I'm going to divide by 1,000. And divide by 1,000 over here. So my T2 is going to be equal to 858 Kelvin. Okay, so I have my T2, but remember, I want to know what it is in degrees Celsius. To do that, I'm going to subtract by 273, and now my answer is 585 degrees Celsius. Okay, again, we can check ourselves to see if that is correct. Remember, we have, sorry about that, if our temperature is, if our volume is 1,000 and we go to 1,500, our volume has gone up. Therefore, my temperature should go up. So I went from 572 to 585. They both went up, so we're in good shape. Okay, so Charles' law is how temperature and volume are related to each other, a direct relationship. See you in class. Bye.